So I decided to use this word symbols or symbolizing this idea. We started with the numbers, and then we're looking at the algorithm and instruction, and we symbolize it with F and G, and we're dealing with the symbols, just like we deal with X and Y that represent numbers, and then we learn the algebra out of it. So the goal is that we're going to symbolize the things that we created, and then think about how to add those symbols and how to multiply those symbols and stuff like that. In a most extreme way, if you think about an idea A and if you think about idea B, we do this a lot and then create a different idea. The process of creating this given two ideas determines how we're going to symbolize this new idea that is created here. Alright, what we're really going to be doing here is this operator. So instead of having a bag of numbers here, we have bag of functions. It's called the vector space of functions, and here's a vector space of functions. And L is an operator. If you're given a one function, we'll do something, some operations that we can understand, and create another function. Just like we're given a number, we do some familiar operator to create another number. So we can create a picture like this if we have this function f, which function was an instruction or algorithm. It's symbolized already. It's letter f. It's not f of x. It's just f stands for that instruction. And we're going to create new instruction, new algorithm. And we denote this process if we're given a one function, an algorithm or instruction, and we're going to transform that to a different algorithm or instruction. So here's a simple example. If a function f is given, what we're going to do is that this function f is multiplied by this function called x squared and plus the identity function x. If we name that function x by h, this must be called h squared function. So with a functional notation, not x, which is a number, remember x squared, which is also a number. So I abused the notation a little bit here, but what we really mean by this one is a given a function, we're going to multiply that given function to this known function h squared and add it to the function h, where h is given, and f is input function. For example, if our input function is sine x, could be something else, cosine x and all the other functions you know, then what we are going to do from here to create a new function is that we're going to multiply the function x squared to it and then add to x. So that's, if we look at it here, this is really a number because it has x in it. Because of the lack of notation, we're just going to accept this as a functional notation. So the better notation than this one is the following. F is a function, and LF, it's supposed to be new functions generated out of this operator process. So this whole thing, LF, stands for this function notation G, another symbol. To turn this one into a number, you have to plug in a number into a function here. So this would be a better notation, but it is kind of bulky and confusing. Once you understand what this really means, we're going to abuse the notation so that we just use this one, L bracket F. It means the function whose values are computed by this formula, x squared times sine x plus x, which is a number. Let me introduce another important example of operator, which is this composition operator. Remember what distinguished this example and this example from the earlier example, it involves the familiar arithmetic. But here's a slightly different process. You don't have this operation for numbers. If you have two numbers, this is different from a multiplication. Remember, there's a circle. This is a composition notation. So if we're given a function, if that makes sense, we can compose this two function to a function to itself. So if f of x is this linear function 2x plus 1, then what this operator does to this function is composing to itself like this. So first you calculate f of x, which is 2x plus 1, and you apply 2 times to that input plus 1 again. So it becomes a 4x plus 3. So this operator takes this function f and change it to 4x plus 3. You may attempt to connect this operation to realize that what happened to this function 2x plus 1 to 4x plus 3 and try to come up with a simple arithmetic that does it. But if you try that same arithmetic and to other functions, then you may realize that it's not that simple. So this operator is not something you can simply do some arithmetic like this one and identically equal. So this is a fundamentally different operation that is done on that space of function. So once you have that space of functions, we have all the 4 arithmetic, and plus we have this interesting operation called composition. In the study of algebra, there's something called the group theory, and that group theory is geared toward to understand this operator defined on that function, space of function. So not much paying much attention to the arithmetic that is defined, inherited from the numbers. For that space of function, one sometimes focus on particularly just this structure defined on the space of function. That part of mathematics is called the group theory. But here we're going to introduce another operators which are